And I'm very excited to present our recent work titled Quantum Depth in the Random Oracle Model. This is joint work with Andrea, Matt, Andrew, Uttam, and Hendrik. Here's a one-slide summary of the talk. The primary question that we ask here is, what is the power of hybrid quantum classical models of computation? One of the motivations for studying this question is trying to understand whether quantum computations can be parallelized. That is, if low-depth quantum computation already captures quantum computation in general. It turns out that many quantum algorithms that crucially use the quantum Fourier transform this includes algorithms for factoring, discrete log, and Pell's equation. All of these algorithms use only shallow quantum depth once augmented by classical computation. So this led Josa to conjecture back in 2005 that shallow quantum circuits augmented with classical computation are actually as powerful as quantum computations. Interestingly, Aronson, in his list of semi-grand challenges, asked for strong evidence showing the contrary. That is, shallow quantum depth is strictly weaker than quantum computation. Aside from the theoretical interest and these conjectures, there's also been a lot of interest in these hybrid models of computation recently, because classical computers obviously are a very mature technology at this point, while applying deep quantum circuits remains very challenging due to the high sensitivity to noise of quantum systems. Further, even for a given quantum depth, performing adaptive measurements is often more challenging. By adaptive measurements, I mean measuring a part of the quantum circuit to determine what subsequent quantum operations to apply. It is therefore important to understand the relationship even among these hybrid models of computation. In this work, we give a comprehensive characterization of quantum depth. We show that under mild assumptions, and I'll explain them later, Josa's conjecture is false, and this also resolves Aronson's challenge. We show that different hybrid models of computation are actually incomparable. And finally, we construct a proof of quantum depth protocol. And what this does is it allows a classical verifier to determine that an untrusted machine has at least a certain amount of quantum depth. And it is important that this proof of quantumness does not have a lot of interaction, and ours is a two-message protocol. Let me begin by describing the models of computation in a little bit more detail. I'm going to consider circuits that take an input of size n. The number of gates in the circuit, or the size of the circuit, is going to be polynomial in this number n. I'm going to be talking about a depth parameter d, and this depth parameter d is going to be at most a polynomial. And for concreteness, one can keep in mind the logarithmic function. So one can imagine that d is a logarithmic function. All right, so the set of problems that one can solve with the simplest d-depth circuit, quantum circuit, is going to be called QNCD for historical reasons. What is a d-depth quantum circuit? Well, it has d many layers of quantum gates, as I've shown. The convention I'm going to follow is that black, to keep the diagram a little bit clean, the black wires indicate So the black wires, carry bits, and the blue wires carry qubits. And I'm not going to draw all the wires, I'm just going to represent them by a single wire. Right, so this is a QNCD circuit. Now, if this QNCD circuit is applied polynomially many times with classical processing interleaved, then the set of problems that this model can solve is going to be denoted by BPP to the QNCD. This notation is suggesting that we are thinking of the classical algorithm as having oracle access to the d-depth quantum circuit. All right. Now let's look at the QNCD circuit again, and this time we allow adaptive measurements. By adaptive measurements, we mean that one can start by doing some classical computation and send the result. So these are the black wires that send the result. Apply a layer of quantum gates. Measure some of the qubits, that's the black wire. Apply another set of classical computation, apply another time some classical computation, use those results to determine the next set of gates, and so on. And the blue wires here, note, is representing a bunch of wires, right, which are carrying qubits. So part of the circuit is kept coherent, part of it is measured, and classical processing is done. Now, this procedure is repeated d many times, so therefore it's QNC sub d to the BPP in the notation, and this represents the set of problems one can solve with this circuit. Now, clearly, if this circuit can be applied once in the lab, it can be repeated polynomially many times. And the set of problems that can be solved with the resulting circuit with classical computations interleaved is denoted by BPP to the QNCD to the BPP. Right? And this is the most general model of depth that we are going to consider, and it seems to capture what happens in the laboratory reasonably well. Let us now look at the basic inclusions because we've introduced a bunch of classes. So here, the first clear, obvious thing is that if you start with a d-depth quantum circuit, right, so QNCD, and you allow for adaptive measurements, then obviously the d-depth quantum circuit is a special case, right? So it's included, and if this QNCD to the BPP is applied many times, as in the BPP to the QNC to the BPP model, then obviously that is going to be contained as well, right? And all of this is going to be contained in BQP. Similarly, one can go the other way. One can start with the QNCD circuit and then repeat it many times. So clearly QNCD is going to be a special case, right? So it's included. And if one adds adaptive measurements to it, then that model is also going to be contained. So these are the obvious containments. In the remaining discussion, we're going to simplify the illustration, and we're going to denote a single layer of quantum gates by a blue bar like this. And the classical computations are going to be denoted by black bars, which are denoted as shown. So this is what the simplified diagram looks like. And whenever we drop the subscript d, we are thinking of d to be fixed as the logarithmic function. And we bring it back to make it explicit when needed to keep the notation clean. All right, so what is known about these circuits, these hybrid models of computation? Joseph's conjecture in terms of these hybrid models can be expressed as follows. So that's one interpretation, which is that BPP to the QNC equals BQP, right? And Anderson's challenge in this notation was that he asked for an instantiatable separation between BPP to the QNC and BQP. So instantiatable we'll come to later. Even finding an oracle separation was already quite challenging, and it was only resolved 2-3 years ago by Chia-Chung Lai and Coudron. They used so Chia-Chung Lai in particular used variants of Simon's problem to show formal evidence in favor of the following statement, which is that these two hybrid models of computation are strictly contained in BQP. In fact, they showed something stronger. They showed fine-grained depth separations. So they showed that they showed evidence for the fact that 2D plus 1 depth hybrid models are strictly weaker than D depth hybrid models. In subsequent work, the relation between these two hybrid models was also studied, and it was shown that these two models of computation are in fact incomparable. They went ahead and showed something a bit stronger. They showed that a constant depth of one hybrid is able to already solve problems that even a log depth of the other hybrid cannot solve. And there's nothing special about log. It can be any fixed function, which is at most a polynomial. The depth can be any fixed function, which is at most a polynomial. The caveat, however, in this particular result was that the oracle they used was non-standard. But the problem was even more pervasive because all of these results that I've mentioned, they use some form of a structured oracle. And with structured oracles, it's often unclear how one would instantiate them. So what does one mean by instantiation? By instantiation, we mean giving an explicit description of the oracle, and somehow it's still being the case that the separation, there's good reason to believe the separation still holds. Because often what happens is that once you give an explicit specification of the oracle, the separation disappears because the description contains too much information which can be exploited to break the the whatever impossibility results that were derived. And in particular, for the Simons problem, there is no candidate construction that we know which preserves the separation that was obtained using the oracle. Additionally, what makes matters a little bit more worse is that we need the instantiation to be depth efficient for any of these results to make sense. For example, the instantiation should be depth polylog. One potential solution seems to be to use the exact opposite, which is exact opposite of a structured oracle, that is a random oracle. And a random oracle is just a uniformly random function. The advantage of using a random oracle is that it admits instantiations. In particular, the random oracle heuristic says that if there is some separation that holds relative to the random oracle, and if the random oracle is replaced with a sufficiently good cryptographic hash function, then the separation would continue to hold, even after having substituted the random function with the cryptographic hash function. And we do have very good constructions for cryptographic hash functions such as SHA-2, SHA-3, and there are also depth-efficient variants. Another thing to say over here is that proving results assuming the random oracle is a fairly weak assumption, and this is because most assumptions in cryptography imply public key cryptography. For example, isogenies, factoring, discrete log, LWE, all of them imply public key cryptography. And in the black box setting, the random oracle provably cannot give public key cryptography. It can give secret key cryptography, but in that sense, it's a weaker assumption. And this brings us to our contributions. So what we do is we show many results relative to a random oracle. So we first show that the hybrid separations that I had mentioned in the previous slide continues to hold, but this time relative to a random oracle. And in fact, the hybrid separations also give separations relative to Q and CD. Sorry, between Q and CD and the hybrid classes. Next, we, instead of considering the hybrid classes that had been considered in the prior works, we introduce and study this new hybrid, which was BPP to the QNC to the BPP, and show that this new hybrid is strictly separate from BQP and from the previous hybrids that had been considered. In fact, what we show is a little bit stronger. We show that a constant depth hybrid, a constant depth of the new hybrid, BPP to the QNC to the BPP, is already able to solve problems that the previous hybrids could not solve, even with log depth or some fixed function D depth. This is strong evidence for the fact that this basically says that the notion of depth that had been considered earlier was inefficient. Finally, we are also able to obtain a fine-grained version of the depth result. So we're able to show that the hybrid model with 2D plus constant depth is able to solve a problem that cannot be solved with D depth, right? And we also have separations from BPP and BQP. So those were our results. What are the techniques we use? To describe them, consider a problem, an oracle problem relative to a random oracle, which is in BQP, and that satisfies classical query soundness. That is, it cannot be solved with polynomially many classical queries. So we define, so we prove a lifting lemma. The lemma says the following: you take a problem P, which I described a few minutes ago, which I described above, and you apply a procedure called D-recursive. So I'll describe the procedure in the next slide, to obtain a new problem P tilde. This new problem has the following properties. P tilde is not in the hybrid model with depth D, and yet P tilde continues to be in BQP. Right? So this already gives us a separation between BQP and the hybrid model. And in particular, if you know that P happens to be in QNC constant, then one can show that P tilde is in the hybrid model with 2D plus constant depth. Right, so this also gives you a fine-grained separation. And what is nice about this particular construction is that it works for any problem P in a black box way, as long as it satisfies this classical query soundness requirement. The next lemma allows us to compare the different hybrids. In this, you start with P and you apply a procedure called deserial, and it will give you a new problem P tilde. And this new problem P tilde will not be in QNC sub D to the BPP, but it will be in BPP to the QNC sub constant whenever P is known to be in QNC sub constant. So this gives the separation between the hybrid models that we had considered earlier. Again, this is a general result. It holds for any problem as long as it satisfies classical query soundness. And to prove the result the other way, that there's a problem in QNC sub constant to the BPP that cannot be solved by BPP to the QNC sub D. This requires much more work, and in particular, to establish this, we prove a structure theorem and for those of you who are already familiar with the area, for a proof of quantumness protocol that was introduced by BKVV, Subrakarsky and others at TQC 2020. And this structure theorem is a crucial strengthening of a result that was presented in STOC about deniable encryption. I'm sorry. So now what I'm going to do is I'm not going to describe the details of these last 2 points. I'm going to spend some time on lemma 1, and I'll describe what this procedure is and how it is used to obtain the separation that we want. So to begin with, we recall the problem introduced by Yamakawa and Zandri in their breakthrough work, which was presented at Fox. They introduced a problem which we call code hashing. This problem was defined relative to a random oracle. This problem has the following 3 properties, which had never been achieved before. First is that the problem is in BQP. Second is that it has a solution that can be verified efficiently, so it's an NP problem. The third is that this problem cannot be solved is not in BPP, so it cannot be solved by a classical machine. And in fact, they show something stronger. They show that it satisfies classical query soundness, the notion that we had mentioned earlier. Okay, so that was the first thing. Second thing is I had not defined the map D recursive. So what is D recursive over problem P? Well, it's exactly the same as the problem P, except that now we want the problem P solved. Instead of being solved relative to a random oracle H, we want it solved relative to a random oracle H tilde, which is just a composition of a bunch of different functions, H0 to HD. What are these functions? These functions are just, again, random oracles, except that their domains are slightly different from the domain and range of H tilde. The crucial point is that one is not given access to H tilde directly. One is only given access to H0 to HD. Okay, and one still has to solve the problem P. And the lifting lemma basically says that the problem P tilde that is obtained by applying this D-recursive map on P is going to be such that the new problem cannot be solved by a hybrid of depth D, but while it can still be solved by BQP. Now, it's straightforward. If we apply this map on code hashing, one immediately gets a problem that is in BQP that can be verified efficiently. It's an NP, but yet it cannot be solved by a hybrid model that has depth D. So what does that mean? That means that a verifier that is interacting with an untrusted prover, if the prover is able to solve the problem, which the verifier can efficiently check because the problem is an NP, then the verifier can be certain that the prover has more than depth D, because no hybrid model with depth at most D could have solved the problem. So this also gives you a proof of quantum depth. Now let me move on to the open questions. The most obvious one is that we would like to relax the classical query soundness requirement. This is because a lot of proofs of quantumness, so until Yamakawa and Zandri, we did not have a proof of quantumness which was only in the random oracle model. Often there are additional assumptions, and the classical query soundness does not allow us to use these other proofs of quantumness. So we would like to increase the list of problems that can be used. The second question is about the decision version of the separations. So assuming a conjecture by Arntzen and Ambainis, those separations cannot hold. However, perhaps there's a way of showing that without assuming the conjecture. So that's an open problem. And in some sense, our results are kind of optimal. Oh, I did not mention. So what I meant to say was that all the results that we have are for search problems. They're not for decision problems. And we don't expect them to hold for the decision problem if we believe Arntzen and Ambainis conjecture. But it's still open whether one can go around having to prove the conjecture in order to show that those results don't hold. Another question is to try to understand the BPP to the QNC to the BPP tower, right? So we considered one level of this tower with like one QNC, but one can conceive of having many different QNC. This would again be some form of a model of hybrid computation with restricted depth. However, it does not look like it captures anything that one would see in a laboratory. Nonetheless, this question is interesting because perhaps there's some rich structure about the different levels of the tower and its relation with the other complexity classes. Finally, there's the question of complete problems. We do not have any complete problem which somehow use the notion of depth. So we do know that there are complete problems in the interactive setting for QMA, for BQP, even for log space. There are complete problems that are known, but nothing that has any connection with depth. And maybe this would help us understand Hamiltonians better. Finally, in the complexity theory direction, we would like to understand the consequences of unconditional separation of the QNC hierarchy. So the QNC hierarchy would just be trying to show that QNCD is strictly contained in, say, QNC2D or QNC some constant times D. The reason why this is particularly interesting is because there are quantum circuits that involve a sequence of Hadamard control Hadamard gates, and it appears that those circuits cannot be compressed. Since they take quantum inputs and quantum outputs, it's not immediate that they have any consequence on the classical NC hierarchy, but maybe there is something interesting to be explored. On the cryptography side, one of the main limitations of our work is that the proof of depth that we have, the honest prover, we could only have it run in polynomial depth, while we would somehow like, say for example, to certify depth T, we would like the prover to run in depth 2D. We don't know how to do this yet. Another question is to try to test for something stronger, a stronger property. For example, maybe we could ask for certifying quantum area, right? So we want to make sure that the machine has both a certain number of qubits and it has a certain amount of depth. Another thing which is of particular interest is to see if one can construct a test that can distinguish machines which have the capability of performing adaptive measurements from those that cannot perform adaptive measurements. This is very similar to the separations among the hybrid classes. However, our separations do not admit an efficient verification. So that question is open. And the last question is a bit more speculative. The notion of depth seems to be closely related to time evolution. And perhaps this could be somehow leveraged to test for indefinite causal structure in quantum mechanics. So with this, I would like to thank you for your attention and encourage you to look at the paper for details, and don't hesitate to reach out to us if you have questions or suggestions. Thank you so much.